Hi, I'm Jack, and this is my report for Lab 1. General idea of this lab is to give us a sense of how much charge everyday objects can obtain. We can explain this using formulas like Coulomb's law, the momentum principle, and the equation for gravity. The reason this happens is because some materials will get a charge when they're in contact with one another, such as Scotch tape peeling away from Scotch tape. The charges will transfer between the two, and then since they're separated, they'll maintain that charge until something discharges them by touching, which will dissipate, and they won't be charged and won't interact. In this lab, we can verify this charging has occurred because bringing a neutral object near a charged object will cause the two to attract, and two likely charged tapes will repel. We find the sign of the tape's charge by comparing it to a known charge, in this case a pen, which we know is negatively charged, so we'll see how they interact. Two tapes, like I said, will repel. We can isolate this repelling force to the y-axis and combat it with gravity. So when they're equal, the tape won't move by the momentum principle, and we can use the force due to gravity in Coulomb's law and the distance to solve for the charge. So to start the experiment, I found the charge tape attracted everything neutral I tried, including paper, book, nylon backpack, and metal scissors. I then rubbed a pen through my hair to charge the pen negatively. This attracted the tape, meaning the tape is positively charged. So then to actually set it up, after ripping each piece of tape off the base tape, I stuck it to my wooden desk so that I touched it as minimally as possible, because if I touched it, it would discharge and wouldn't do anything. The bottom tape is then on pencils for the same reason, and brought them close together until I saw an interaction. At about 1.5 centimeters, they started to repel. So when I had to start doing the math of these numbers, I had to make a few assumptions. Mainly, each tape was a point charge and their magnitudes were equal, and air resistance was negligible. We can make these assumptions in this case just to make the math easy, because we're just trying to get a general sense of the numbers, not super precise. So my tape was 0.2 meters long, weighed 0.0002 kilograms. Like I said, the distance was 0.015 meters. And using force equals mg, gravitational force was 0.002 newtons approximately, because by the momentum principle, we know that the gravitational force and the electric force were equal. The electric force is also 0.002 newtons. Plugging that and the distance into Coulomb's law, I found the charge per tape about 7 times 10 to the negative 9 coulombs. Dividing by E, I found about 4.3 times 10 to the 10 electrons lost per tape. This raises the question, what if protons and electrons had their charges reversed? Nothing, because like charged tapes would still repel, and the pen and the tape would still attract, because positive and negative always attract. So to find the ratio of lost electrons to total atoms, I had to make more assumptions, mainly that the atoms were evenly spread over just the surface of the tape and that the electrons left the atoms evenly. My tape area was about 0.004 square meters, or 4 times 10 to the 17 atoms on the surface. My ratio then was about 1 times 10 to the negative 7 electrons lost per atom, which means that not every atom gave up an electron. This is a pretty reasonable result to me, because if every atom gave up an electron, it would be a very significant change in the charge. So I then wrote this handy-dandy program. So I start by defining some constants, 1 over 4 pi epsilon naught, gravity, the tape density and length. I then calculate the mass and the force due to gravity of the tape. Then visually, I have the two pieces of tape as flat boxes, and then the force for gravity and electric force as arrows pointing in opposite directions, just to get a sense so we know what's going on and how they're interacting. And I have a slider which I can use to set the distance between the tapes. So every time the slider's moved, it calls this function, which, using Coulomb's law, solves for Q, the charge of one piece of tape. It then updates the position of the floating tape and the arrows to that, so they're all aligned. I'll show what that does in a second. And then it prints the distance and the charge per tape. So here's what that does. I have it default to the distance I found, and it on its own calculates exactly the same charge that I did, so this program is working. So if I increase the distance, the charge has to go way up, which makes sense. And if the distance is 0, then there's no charge, which makes sense. So this kind of ties everything together, Coulomb's law, this demonstrates how the bigger the distance, the bigger the charge has to be, which is what this lab is about. So thank you for watching.